Alright, let's talk about integration by parts. This is going to be one of the very most commonly used techniques that you're going to use when integrating Riemann integrable functions. And yeah, let's just get right into it. So the formula here is quite simple. I'm going to teach you a different method of doing this after we go over the formula method. It's called the column or tabular method, whatever you want to call it. But we'll start off with the origins. So if we have an integral of u dv, then this is the equivalent of uv minus v du. Okay, so this is our integration formula. So what does this mean? Well, what we need to do is if we have a function, we need to choose something to be used. So let's say, so this is a what do we call it? This is let's just say an anti-product rule. You know, you kind of, so you know how we have like the derivative of x to the n is n to the x times to the n minus 1, n times x to the n minus 1. Well, we now also have the counter power rule, or the reverse power rule, where we have x to the n plus 1 over n plus 1. So in these two cases, it's kind of like they're opposites of each other. And just like how the use substitution method is the reverse of the chain rule, this is the reverse of the product rule. So if we have a integral of some function, we essentially need to choose one function to be u, one to be dv, and then we need to say, okay, u is equal to f of x, so du is equal to f prime of x dx, dv is going to be g of x dx, and our v is just going to be the integral of this, so you could say maybe cap g of x, and you can, and the reason I chose the entire dx part, this element is also included in the dv, is because we're going to get that dx part back from the differentiation of u, but that's just a little small thing. And then you're obviously going to apply this to the formula, so we're really saying that this is equal to uv, which is f of x times cap g of x, minus the integral of cap g of x times f prime of x. And what you're hoping for is that when you get to this stage, you're hoping for this integral to be an elementary integral, something that you can do very easily. Or maybe you can use u sub, or just something that can get you a nicer solution as opposed to trying to do something else with this. So yeah, that's the entire idea, and let's take a look at a very common example here. So let's say I have the integral of x squared e to the x, or actually we're going to start with x e to the x dx. So why can we not use u substitution here? Because if we let u equal x, well, du is just dx, and there's no, this can't be canceled out. So there's nothing really to do here. In another way, we can actually now just apply the formula that we just learned, right? So we can now just use integration by parts. So let's let u equal x, du is equal to just dx, right? We have dv is going to be e to the x dx, so our integral is just going to be this, which is just going to be e to the x. And don't worry about the plus c. The plus c is going to come back, and if you actually did put a plus c, it will cancel itself out. And there's a derivation video that I will do that showcases why the plus c is irrelevant for this step particularly. So let's do our formula. Remember, it's going to be uv minus integral of v du. uv minus integral of v du. So uv is just x e to the x minus integral v du, which is e to the x, and dx, right? So we have, I'll just label it, right? This is our all of our things. So we have our u, we have our v, minus we have our v, and then we have our du. And whatever you choose to be dv is never going to show up. So that's something you might want to notice. And now you see from an integral that we couldn't solve earlier, this integral, and I don't know why it's keep doing that, this integral here, now we can solve this because the integral of e to the x is just e to the x, and we just plug on the plus c. So you plug in the plus c after you do all the integration by parts stuff at the very end. So there you have it, and we see that we can now integrate these more complicated functions and turn them into easier ones using this formula. So let's do a different problem. Let's say we have the integral of x squared sine x dx. So obviously u sub is completely out of the picture here, so there's no need to do u sub. So we're going to use integration by parts. So we're going to let u equal x squared. We're going to let du is equal to 2x. Now, you might be wondering, why am I choosing the polynomial to differentiate? And here, that's a great question. And you'll see why after we do this example. So just keep that in mind. There's a reason I'm choosing the polynomial to differentiate first. We have our dv is just going to be sine x, and v, the integral of sine x, which is just negative cosine x. Okay, and we of course have the dx over there. Okay, so plug in the formula. uv, so u is x squared, v is negative cosine x, so I'll rewrite it like that. And of course, keep the equal sign very consistent. So negative x squared cosine x minus the integral of v du. V is negative cosine x, du is times 2x. So I'll rewrite this a little bit more nicer, so we can bring this negative outside of the integral, so it's plus. We can even bring out a 2, and it's going to be x cosine x. Now, what's the problem here? We've done everything correctly. So why can't we, why isn't this easier? Well, that's because we need to do integration by parts again for just this integral. Okay? So, in other words, I'm going to highlight this step. So this integral itself in blue. Okay? So, now we need to do the same thing again for this integral. So we're going to let u equal x. So du is just dx. dv is cosine x. dx. v is sine x. Right? Integral of cosine is just sine. So now this is equal to 2 times all, we factor out our 2. And uv, which is x sine x, minus the integral of v to u, which is sine x times dx. Okay, so now we can finish the rest of the problem because this part is doable. So I'm going to rewrite everything. So we have, remember, negative x squared cosine x plus, and then we have our 2x sine x minus integral of sine x dx, right? So this is what we're evaluating. And of course, it's just going to be plus 2x sine x minus, and then integral of sine is just negative cosine, but it's going to become positive with that minus sign, so it's going to be 2 cosine x. And now we tag in our plus c, and we're done. So why did I choose the polynomial to differentiate? Or why did I choose the polynomial to be u? Well, the reason is, notice in this specific integral, we had to do integration by parts multiple times. Now, if we didn't choose, well, first of all, if we let the polynomial be u, eventually, after differentiating it a certain amount of times, right? because we let u equal x here when it was in the first degree, we notice that because the polynomial is eventually going to differentiate into a constant, and the other term, the dv and the v, it multiplied to that constant, it doesn't really affect the integral itself. It makes things easier. Think about it. X squared is going to turn into 2x, which turns into 2, and which turns into 0. Eventually, if you choose the polynomial to integrate or differentiate, eventually you're going to end up with, because you have a uv minus v du, that du term, this what we have here, this du term is eventually going to turn into 0 or a constant. So if you let the polynomial be u and you keep differentiating it, you're eventually going to stop somewhere. Now this of course doesn't work with integrals that you don't know, such as ln of x. Right, like how would you do this? We're going to find out how to do this in a second, but as of right now, you have no idea how to do that. So you can't, because if you let dv equal ln x, what's the integral of ln x? You don't know. Not yet. Okay. Now, before we move on to the next example, notice how this took kind of a long time. So we're going to do a different method. So we're going to do the same integral, but now we're going to speed it up a little bit. So integral of x squared sine x dx. We're going to do something called the tabular method. Okay, so here's how it works. You're going to create a chart with d and I. It's called the di method for those of you who watch 3 Blue 1, sorry, not 3 Blue 1 Brown, Black Pen, Red Pen. That's what I'm thinking of. So di method. And what we're doing here is we're choosing one function to constantly differentiate and one function to constantly integrate. Okay? So, in this case, like I said, 99% of the time, you're going to choose the differentiating factor or the u term, with quote unquote, as the thing you're going to differentiate or let be u. So yeah, we're going to put x squared here, and we're going to choose, of course, the other function to integrate, sine x. Now, here's what we're going to do. We're going to differentiate x squared until it gets to 0. The di method works because the polynomial differentiates to 0. So this is going to be 2x, this is going to be 2, and then 0. Okay? So it stops there. Once it hits 0, it stops. And what we're going to do here is we're going to put a plus sign for the first term, or the first row, which is going to be what you integrate. And we're going to alternate the signs like this. And we're going to multiply these very soon, and you'll see what happens. Now for sine x, we're going to integrate it until we get to the 0. So however many times you differentiated the polynomial to get to 0 is how many times you're going to integrate. So in this case, we have negative cosine x, negative sine x, and cosine x. And we stop there once it matches with the 0. And now here's what we're going to do. We're going to multiply diagonally like this until you can't go with another diagonal, right? Because the 0 doesn't have another diagonal. So you stop here. And we're going to multiply diagonally with these constants, with these signs, okay? And you'll see what happens. So, and I'll do it in different colors. So this is blue, this is red, and this is whatever this color is. So, according to this, it's going to be equal to negative x squared cosine x, right? And there's a plus, so no need to multiply. And then we have a minus and a minus. So it's going to be minus a negative 2x sine x. And then our last term is just going to be plus 2 cosine x. And that's it, right? And we can rewrite this, of course, as just negative x squared cosine x plus 2x sine x plus 2 cosine x. And once you're done, just tag on the plus c. And look at what happened here. This is the same answer as the one we have up here. We have the same answers, guys. Look at that. These two are the same. So, oh, we have a minus 2 cosine x. That's weird. No, this should be plus. Sorry, guys. But anyways, we see how this method is so much simpler. I mean, look at all the work we had to do for that, and look at this one. So we see that we can save a lot of time. Now, because I was explaining this to you, obviously it took a lot longer, but now you can see we can do stuff a little bit faster. So let's take the integral of x cubed e to the x dx. Oh, it's the third power. That's okay, we're going to go straight to the di method. So x cubed e to the x, so 3x squared. Then we have 6x, put this a little bit higher. Then we have 6, and we have 0. And e to the x is just always e to the x, so it's very nice and simple. And we're now going to multiply diagonally. So this goes to this, this goes to this, this goes to this, and this goes to this. And of course we have our plus, minus, plus, minus, plus. Super important. So now we can do our little steps. So x cubed e to the x is the first diagonal. It's going to be minus because of that. So minus 3x squared e to the x plus 6x e to the x minus 6e to the x. And we're done. That's it. We have a plus c, and that's it. Nothing more to be done. Took like 2 seconds, guys. So easy. All right. Now, what if I asked you, okay, how do you find the integral of ln of x? So up until now, you didn't know how to do this. You can't use u sub. There's no elementary formula, or there really is, but it's not like, oh, ln x is 1 over x, sine x is cosine x. It's not like those derivative rules. In this case, we have to use integration by parts. So I'm going to show you how you can do this both ways. So we're going to start off with the formula method. So in this scenario, because we don't really have a polynomial, the di column method or tabular method doesn't really work. So we have to stick with what we know from the formula. So u equals ln of x, du will then be 1 over x dx. But wait, hold on. What's our product? We have to have a u and a dv. Well, if you're smart, then you can really say that this is the same thing as this, right? So it's a little bit sketchy, I know it's a little bit, but it's really just 1 dx. So v will then be x. The integral of a constant is just that constant tagged with an x. So let's do our formula. So it's going to be uv, so x ln x, minus the integral of v du, which is just going to be x over x dx. So this is really x ln x minus the integral of 1 dx, and of course x, this just turns into minus x, and we tag on a plus c. So the integral of x of ln of x is just x ln x minus x. Lots of x's. Okay, so this is how we can use integration by parts to derive such an integral. So now let's go back to that integral I mentioned earlier. And let's see what happens here. Well, if we let d, the differentiating factor, be x squared, well, yeah, the polynomial is going to go to 0, but this is as far as I think any of us can really go. Beyond this, after showing this, mean, integrating this guy is not even, I'm not even going to touch that. So we have to do something else. So we're going to do DI method. Well, and yes, you can use UV method. It will work as well. But we're going to do DI method, and you're going to see, okay, when the differentiating factor is not a polynomial, well, it's still doable. You just have to be smart about when you stop. I'm going to stop at 1 over x. I'm going to do this one time. So therefore, this is going to be our new table. We have our plus, we have our minus. Okay, so let's do it. This diagonal, right? So we have 1/3 x cubed ln of x. Okay, and now we can't do any more diagonals, but we're not at 0, so there's nowhere to stop. And this is never going to turn into 0. But we're going to multiply horizontally and integrate their product. So it's going to be minus the integral of 1 over x times 1/3 x cubed dx. Think of this last row as your integral of v du part of the formula, right? Because that's really what you're doing, guys. This is our u, this is our dv. Let's do it, right? If you let u equal ln x, du is just 1 over x dx. You have a dv, which is x squared, and v is 1/3 x cubed. Look at the symmetry of the formulas. uv, so this is our, we have our uv, and then we have our v du, which is right here, the integral of v du. So we can apply the idea of the formula here. So you can literally, for non-polynomial differentials, stop after one row and try integrating the product of the horizontal product of the last row. Okay, so this is really just 1/3 x cubed ln x minus the integral of, and this is going to be x 1/3. We're going to bring that out, and it's going to be x squared. The x's will cancel out 1 degree. And now you see, okay, this is now doable. So it's 1/3 x cubed ln of x minus 1/9 x cubed. Hopefully you guys saw where I got that, plus c, and there's our integral. So we use the tabular method by just differentiating the non-polynomial term one time and integrating horizontally of the last row, which is really doing the same thing here, guys. Okay? Awesome. Now there's one more case that you guys need to watch out for. So we've done a lot of different cases. We have a case where you can't let the polynomial be the differentiating term, or the u term. In this case, we had to make ln of x do that. In this case, we had to think of the integration by parts as a product of 1 and the function, whatever else the function is. Okay? In this method, we just showcase the powerfulness of the DI method. And this is our standard integration by formula, right? And certainly you can, these are all great examples, but there's only one more example that, might trick you up. What if I have the integral of e to the x sine x? Now, why is this a problem? Let's think about this. Well, your idea is, there's no polynomial anywhere. In fact, no matter what you differentiate or integrate, whatever term, e to the x or sine x, you're not going to get any sort of x to some degree. These are both transcendental functions. Okay, so in fact, what we're going to do here is we're going to use the formula method, and we're going to do it 2 more times after the first one. So a total of, I believe, 3. Or actually, I think it's just 2, but I don't know. We'll see. So what are we going to do? Well, me personally, I'm going to let u equal sine x. I think integrating e to the x is much more simpler than integrating sine because you might get them signs wrong, right? The negative, positive. So dv is just e to the x dx. So du is just cosine x, then v is just e to the x. So let's do the formula. uv, which is e to the x sine x, minus the integral of v du, so e to the x cosine x. Okay. So we kind of made it more complicated. We have just the same integral with cosine. But we're going to do it again. You'll see what's going to happen here. So we're going to let u equal cosine x again, this time, letting the trigonometric term be u. So du is negative sine x dx. dv, of course, is just e to the x, and here we have v. So this is really equal to e to the x sine x minus uv, which is e to the x cosine x, minus the integral of v du, which is e to the x times negative sine x. Now I'm going to simplify this a little bit further. And there's triple negative here, so it's still going to be negative. Okay, so we got to this step. And yes, we've made it extremely complex now. But notice something here. What is this? This is our original integral. It's the same as this. Okay, so remember, this entire thing is still equal to the integral of e to the x sine x dx. So now just look at this equation, right? This is our equation. What do you think we can do? Well, we can add. So I'm going to rewrite this in this way. So we're going to have e to the x sine x minus e to the x cosine x minus integral of e to the x sine x is dx is equal to integral of e to the x sine x dx. We can add this to this side, so we're going to get e to the x sine x minus e to the x cosine x is equal to 2, because these are both the same thing, 2 times the integral of e to the x sine x dx. And wait, if we divide by 2 now, by both sides, all we have is e to the x sine x minus e to the x cosine x, all divided by 2, which is equal to the integral of e to the x sine x dx. And all we have to do now is just tag on a plus c, and this left-hand side is our solution, because this is the integral we were looking for at the start of this, right? This is the same thing. So this is our final case. We have a looping integral where we're going to eventually return to the original integral, and we're going to do some equation manipulations. So we had to notice that we can set this equal to e to the x sine x itself, and notice, oh, we have the same two things, so we can combine them. Now, how would I do this with the DI method? So unfortunately, unless you're a kind of a genius and you saw this coming somehow, in order to do this, you would have to first differentiate until you got to the third term. Of course, integrate that many times, plus minus plus, and you do the same thing diagonal. So e to the x sine x minus e to the x cosine x minus, and then of course we talked about that horizontal product case, so minus integral of, which is going to be e to the x sine x and dx, and we're really saying that this is equivalent to e to the x sine x dx. So you could have gone to this step faster, but there was really, it's a little suspicious if you did know how to do this, because you would have to know when to stop. And yes, you can argue that, okay, in a case where you have a looping trigonometric function and a different looping transcendental function, you're eventually going to return, because trigonomic function derivatives for sine and cosine eventually return to each other. They alternate. One is sine, the next is cos, the next is sine, next is cos, right? Maybe with different negatives and positives, but still. So you can kind of argue, but in my opinion, I don't think this method is very viable, but it's still there. But anyways, if you were to do this, or given this type of integral, maybe instead of sine it's cosine, you would just do the same thing, just use the formula method. But so those are all the cases for integration by parts that you're going to pretty much need to know for Calculus 2 or Calculus BC. So yeah, there you guys have it. So have a great rest of your day.